Okay, picture this. Something truly terrifying on a cosmic scale. A star, maybe way bigger than our own sun, just getting stretched, pulled
Okay.
apart by some invisible
It
force.
sounds like fiction, doesn't it?
Totally. But it's real. It's what happens when a star gets, well, a bit too close to a supermassive black hole.
And the James Webb Space Telescope, JWST, is finally letting us see these things properly.
Exactly, especially in places we just couldn't peek into before. Welcome to the deep dive. We take all the latest research, the surprising finds, our notes.
And try to make sense of it all.
Right, distill it down. Today we're looking at these, well, violent cosmic feasts using this amazing new JWST data.
Yeah, the mission really is to figure out how these supermassive black holes actually behave, especially the hidden ones.
The ones lurking in those really dusty, murky galaxies. And here's the kicker, the big reveal. JWST seems to have found black holes that, well, they wait patiently before they gobble up a star.
Which is really different from the ones we thought were just constantly feeding.
Right. Completely different. These are the first JWST sightings of these tidal disruption events, or TDEs. And one scientist said they look nothing like what we've ever seen before.
Wow, okay.
So if they're just waiting, what does that do to our old ideas
Yeah.
about how these things work?
Well, it kind of flips the script. We often pictured them as, always hungry, like cosmic vacuum cleaners just sucking up everything nearby.
Yeah, constantly active.
Exactly. But this suggests maybe a lot of them are quieter, more like ambush predators, just sitting there dormant until, bang, a star wanders too close.
An ambush predator. That's a great image.
It really changes how often we think these things might be happening and, well, just their whole feeding style.
Okay, so that's the big picture shift. But let's get into the main event itself, this tidal disruption event. What exactly is a TDE?
Okay, so fundamentally, you've got a supermassive black hole, usually right in the center of a galaxy.
Right?
And if a star passes too close, the black hole's gravity is just immense. It literally tears the star apart, shreds it.
And that causes
A huge blast of energy. I mean, a really, really bright flare. It can actually outshine the entire host galaxy for a while.
incredible. And this leads to that amazing, slightly horrifying term, spaghettification. It sounds made up.
It does. But it's the real scientific term, believe it or not. It describes exactly what happens.
So paint that picture for us. How does a star become spaghetti?
Okay, so the star gets close to this massive object, right?
Yeah.
Millions, maybe billions of times the mass of our sun.
Mind-boggling scale.
Totally. And the gravity pull on the side of the star closer to the black hole is way, way stronger than the pull on the far side.
Okay, a difference in pull.
A huge difference. And that difference, the tidal force, stretches the star vertically like pulling taffy, and at the same time, it squashes it horizontally. So you end up with this long, thin stream of star stuff, hence spaghetti.
Stellar spaghetti. Okay, so once you've got this cosmic pasta, what happens next? Does it just fall straight in?
Not usually, no. It doesn't just plummet in. Instead, this shredded material starts swirling around the black hole.
Like water going down a drain.
Sort of, yeah. It forms this flat, spinning disk. We call it an accretion disk. And as the material spirals inwards, it gets incredibly hot and glows super brightly. That's a lot of the light we see.
So the disk itself is glowing as it feeds the black hole?
Exactly. But that's not all. Some of that material doesn't fall in. It gets funneled towards the black hole's poles
Okay.
and then shot outwards at incredible speeds. These are the high-energy jets we sometimes see.
Ah, right. So you get light from the disk and from these jets.
You got it. Both contribute to making the TDE so incredibly bright across different types of light, like X-rays and optical light.
The energy involved is just staggering. Now, JWST is giving us this new view, but TDEs themselves, they aren't brand new discoveries, are they?
No, not entirely new. Astronomers have known about them since the 1990s, actually. The first one was spotted by an X-ray satellite called ROSAT.
Okay.
And since then, maybe about 100 or so have been found before JWST came along. But there was always this nagging problem, a blind spot.
Right. You mentioned the dusty galaxies earlier. That was the issue. We just couldn't see into them.
Precisely. Dust and gas are really, really good at blocking visible light and X-rays. They just absorb it.
Like cosmic fog.
Exactly like cosmic fog. So if a TDE happened inside one of these really dense, dusty galaxies, the flash would happen, but the light just couldn't get out to our telescopes. We were missing them.
Hidden violence. Which brings us to why the JWST is such a revolution here. What's its superpower?
Infrared light. That's the key.
Okay, explain that. Why infrared?
Well, infrared light has longer wavelengths than visible light or X-rays. And those longer waves are much better at slipping through clouds of dust and gas without getting absorbed or scattered.
Ah, so it can see through the fog.
Pretty much. And JWST is just the most powerful, most sensitive infrared telescope we've ever built. A $10 billion eye in the sky. Basically designed for exactly this kind of challenge. You can see things that were literally invisible before.
Incredible. So, okay, it can peer through the dust. How did it actually confirm these were TDEs? You mentioned a fingerprint.
Yeah, a very specific infrared fingerprint. It's quite clever, actually. When the black hole is feeding that accretion disk we talked about,
The glowing disk.
it blasts out tons of high-energy radiation. And when that radiation hits nearby atoms, it can knock electrons off them. It ionizes them.
Okay, it charges them up, basically.
Sort of, yeah. And specifically, when it ionizes neon atoms in a certain way, those neon atoms release infrared light at a very, very specific wavelength, a signature.
A neon sign saying black hole eating here.
Basically, yes. The lead scientist, Megan Masterson, she said, there's nothing else in the universe that can excite this gas to these energies, except for black hole accretion. It's undeniable proof.
Wow. So, did they find this neon sign?
They did. They looked at 12 places where they suspected dusty TDEs might be happening. And they found this specific neon fingerprint in 4 of them.
4 confirmed hidden TDEs.
Yep. And one of those is actually the closest TDE ever found to Earth, only about 130 million light years away, which sounds far, but cosmically.
It's practically next door. So, finding these 4, that suggests there could be many, many more hidden out there, right?
Absolutely. It implies that our previous counts of TDEs were probably way off. We were only seeing the ones in relatively clean, dust-free galaxies.
So these violent events could be much more common than we thought.
Much more common. It really opens up a whole new population of these events for us to study. It's a major shift.
Okay, so they found these hidden TDEs. But that raises another question. Were these black holes already active, constantly snacking on gas and dust? Or were they quiet, sleeping giants that just woke up for this stellar meal?
That was the next big question, exactly. Were these active galactic nuclei, AGN, that just happened to grab a star? Or were they genuinely dormant black holes?
And could JWST tell the difference?
It seems so. It looked at the patterns of dust around these black holes. See, normally active galaxies, the ones that are constantly feeding, tend to have these specific structures, like clumpy donut-shaped dust clouds around the central black hole.
Okay, a typical active black hole has a dusty donut.
Kind of, yeah. But in these 4 dusty galaxies where they found the TDEs, the dust patterns look different. Not like the typical active ones.
Different how? Less structured.
Yeah, the observations didn't match that standard active galaxy profile. And that difference is the key.
So what does that difference imply?
It strongly suggests that these black holes weren't active before the star arrived. They were indeed dormant, lying in wait.
Wow.
As Masterson put it, combining the neon signal with these dust patterns, the only thing these flares could be are TDEs.
So it confirms they were quiet until dinner time. And she also said something about being able to study the dormant environment itself now.
Right. That's another really exciting part. Because these black holes were dormant before the TDE lit things up, JWST is actually giving us a glimpse of what the neighborhood around a quiet, dormant, supermassive black hole looks like in these dusty galaxies.
We're seeing their normal, quiet state for the first time in these environments.
Exactly. Not just seeing them when they're actively feasting, but understanding their baseline. It's a whole new perspective.
Amazing. So we have this powerful new tool. We're finding these hidden events. We're learning they happen to dormant black holes. What's next? Where does this research go now?
Well, the obvious first step is just find more, detect more of these hidden TDEs, build up a bigger sample size.
And what will having more examples tell us?
A whole lot, hopefully. We can start figuring out fundamental stuff about the black holes themselves, like how fast are they spinning, how massive are they really, and also how efficient are they at eating? How much of that star material do they actually swallow versus how much gets blown out in those jets we talked about?
Right, the cosmic digestion process.
Pretty much.
Yeah.
And also, how long does the whole feeding frenzy actually last? Masterson pointed out it's not an instantaneous process. The black hole takes time to consume all that stellar spaghetti.
So we can study the whole timeline of the meal.
Hopefully, yeah. With more data, we can track the brightness over time, see how the environment changes. It's all about building a clearer picture. But it's early days.
Still a lot of unknowns.
Oh, definitely. As Masterson said, no one knows because we just started discovering and studying these events. It's genuinely the frontier of this research area.
That sense of discovery must be incredible. And just for context, this work we've been discussing, it was published in the Astrophysical Journal Letters back on July 24th.
That's right. Hot off the presses, relatively speaking.
So let's try and wrap this up. What are the big takeaways for you listening at home?
Well, first, JWST is like X-ray specs for dusty galaxies, letting us see things like TDEs that were totally hidden before.
Right. And second, there's this unique neon fingerprint, a specific infrared signal that screams black hole feeding.
Yep, undeniable proof. And maybe the biggest surprise
is that many of these black holes hidden in the dust seem to have been dormant, just patiently waiting for a star to wander by, not constantly active like we might have thought.
Exactly. It changes our census of TDEs and gives us this amazing new window into how quiet supermassive black holes live most of the time. It's crucial for understanding how galaxies evolve.
It really is. Which leaves us with, maybe, a final thought to chew on. Just think about the sheer scale of the universe and how much is still hidden.
Yeah.
If an event as powerful, as incredibly bright as a star being torn apart by a black hole can be hidden so well by simple dust, what else is going on out there? What other amazing, maybe even stranger cosmic events are happening right now, completely invisible to us, just waiting for the next breakthrough, the next telescope to finally bring them into the light?
Makes you wonder, doesn't it? The universe definitely still holds its secrets close.